So today's learning goal is, can I explain and apply Pascal's triangle to a variety of real-world applications? So here's an example of Pascal's triangle. There are a few key concepts that you need to understand about the Pascal's triangle. One, at the end of each row, there is a 1. Okay. The other thing that you'll know is that all of the interior numbers are computed by adding the two numbers above them. Okay, so in order to do this, we're going to have to go and construct all the different rows for Pascal's triangle. The other thing that I should let you know is that 3, the top of the triangle has the number 1, i.e. it is the first, or was it the 0th row? I think I said it was the 0th row. So we're going to go and calculate Pascal's triangle from all the way to row number 8. So we'll start by writing row number, and we'll start from 0, 1, 2, 3, 4, 5, 6, 7, and 8. Now make sure you move over to the right a little bit, because this kind of gets unwieldy very quickly. So in row 0, we start with the number 1. Remember, at the end of our rows, we should have a 1. So the next row, you're going to have a 1 and a 1. Okay? Now, the same will be done for row 2. But remember what I said. The interior numbers of our triangle have to be calculated by adding the two numbers directly above. So in that case, we're going to go and take 1 and 1 and add it to get 2 in the center. And now we go and set up our next row. 1 and 1. And we have to add up all the numbers directly above to get the internal numbers. So in this case, 1 plus 2 gives 3, and 2 plus 1 gives 3 again. And we repeat this for the 4th row. So now, 4th row, 1 and 1. So the numbers directly above this part here is, the numbers above this is right here, 1 and 3. We're going to add those to get 4. And then 6, and then 4. And we repeat the cycle over and over again. Okay, now that we've created that entire list, you'll notice that if I highlight the information that's on here, you'll be absolutely amazed. Going down the outsides of the triangle, you'll notice the following. You'll notice that on the diagonals of the triangle, here and here, the numbers that are to the outside of the triangle are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and that's it, really. Okay. There's also another thing that's impressive about this triangle. Once you do that, all we're doing is just looking for certain things. Now, think of the first row as what would happen if you had absolutely no possibility of moving from something. We call that a choice. Each row represents the number of choices that you have. So if I was looking at the next choice, let's say I was in a room and my door was locked and I couldn't get out. All I could do is stay. But let's say I had the key to the door, but I was in the room. I have a choice to either stay or go. And that is what Pascal's triangle essentially helps us to understand. It helps us to understand the number of choices that we have depending on a situation. So now what I'd like you to do is I'd like you to recognize something about each row. If I total all the numbers in each row, which I'm going to do over here, the total, right? So the total here is, the total for the first row is 1. The total for the second row is 2. The total for the third row is 4. The total for the third row is, oh my goodness, it's 8. Total for the fourth row is 16. Total for the fifth row is 32. And then 64. And then 128. And then 256. Now here is the relationship for each row. If I was using the row as an indicator. 2 to the exponent of 0 is our relationship to get 1. 2 to the 2 to the 1 is 2. 2 squared represents the total amount of ways something can be chosen. Same thing again. 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, and 2 to the 8. So remember, think of it this way. If I have no choices, I really only have one. If I have one choice, I have a choice to stay or go. If I have two choices, I could stay. If I had two choices, what would happen is I could stay, go into number 1, or go into number 2, or do both, right? It's kind of weird how that works, but it's how we relate all of the total possibilities that we have in each row. So this helps us to count very difficult tasks. All right, so let's move on to the main topic of the day. What does NCR mean? When you hear NCR, this is what you mean. NCR means it's the notation for a combination. So what does NCR mean? It's the notation for a combination. We can write it as NCR, and sometimes you will see it written as this. NR, where N is our number of choices and R is the specific choice that we choose. Okay, so think of N as the number of objects. And R to be the objects chosen in order. So, i.e., the number in objects chosen. And in this case, order doesn't matter. Okay. So now, what's the formula for NCR? Remember, I'm going to give you a bunch of different ways to represent this. You choose which one you want. So I would say this. You'd go NCR is the same as, well, we could go C of NR. Maybe you guys like it this way. So that's another way to represent it. Or you can write it as NR. Now, in mathematics, you would say, in mathematics, I would say N choose R, if you ever saw it. So here's what the formula is. The actual formula is, let's call it CNR is equal to n factorial divided by r factorial times n minus r factorial. Now, what you need to understand is everyone that has a scientific calculator can use this function on your calculator. So it's not as bad as one might think. Now, let's go and take a look at what the connection is between NCR and the Pascal's triangle. Let's do that right now. So let's go to our Pascal's triangle and copy down our triangle, and we'll copy it down to the fourth column. So sorry, I meant fourth row. So every row represents the total number of possibilities that I have, i.e. the n value of NCR. Okay? And what this means is, it means that if I choose a certain number for NCR, for the R value, we get one of the numbers in our table here. So imagine you have the combination, you say, okay, C of 4, 2. On your calculator, you would use something like this. You would punch in 4, then you would hit Shift, and then find the NCR button, NCR button. So Shift, NCR, and then 2. And you're going to get the number 6. Okay? Now, if you're not comfortable with that, you could write it as you see here. Use that formula to write it out, and use the factorial button on your calculator. Now, let's go over where we find the number 6 in here. You'll notice here is the number 6 in the center of our chart, but you'll notice it's in the fourth row. So in the fourth row of the Pascal's triangle, if I have four objects and I choose 2 of them regardless of order, I have 6 possible ways. That's all it is. Though this says 6 arrangements. So if I had a bag of balls and there were 6 balls and 2 of them were identical, okay, i.e. 2 green balls that you couldn't distinguish, you would take 4 balls, put 2 of them in which would be green, and you pull them out, there'd only be 6 arrangements. That's it. That's all it's saying. We'll have time to practice this stuff in class. So there will be a lot of confusion at the beginning, but we will get through this together. So again, let's go back to what the connection is between Pascal's triangle and the NCR or CNR. This is no more than a roadmap of Pascal's triangle. Okay, so it literally will find different positions in the triangle for us. And by doing so, it will help us calculate the number of arrangements for different concepts. All right. Okay, so now let's move on to calculating NCR by hand. Let's make sure we understand how to do this. The first thing you need to understand is when we are using Pascal's triangle or NCR, the C, if I have C of NR, it really means C is the row in Pascal's triangle and the term number, i.e. the zeros, the first, the second, the third, the whatever. Okay? So now let us calculate NCR. So NCR, or I'll call it C of NR, is equal to N factorial divided by either R factorial, so R factorial times N minus R factorial. Okay? And what that does is it just calculates it quickly for us. That's all. So right now, we're about to start understanding how this stuff works. This next part of the lesson will take 8 minutes. All right, so now how do you evaluate this with a calculator? Okay. What we're going to do is we're going to take a look at two possible calculations here. So let's say I have a C of 21.7, okay? You're going to get 116,280. And how did we get that? On your calculator, you're going to go and type in 21 on your calculator. Then you're going to hit Shift. You're going to find the NCR function. So you hit Shift and NCR, and then you hit the number 7. And that is how you calculate it. So try this one. C is equal to 3019. Okay? All right, 3019. Punch that in your calculator, see if you get the same as me. And you get 5, 4, 6, 2, 7, 300. You know you've got it. All right, let's work on this next problem. How many different ways are there to get from A to B? Now, I need you to remember that you're moving to the right and down in order to continue to make progress. All right, so here we go. Let's take a look at this. So we're in position A and we need to get to B. So moving along this first say grid, i.e. maybe it's like a roadway or something like this, there's only one possible way to move along that roadway. And then the same can be said for this one here. Okay? As a matter of fact, let's do this a little differently. I'm going to draw this a little differently so it kind of makes sense to you now. So imagine that you take this graph and identify where you want to start and where you want to end. Each one of the vertices on this graph have a certain value that's assigned to it. So if I go from this point to this point here, there's only one way that I can get there. The same can be said for this point, and this point, and this point, and this point, and guess what? This point. So there's only one way to get there because you can only go right every time you move down the line. There's only one way to get there. Okay? So now, here's what I need to ask you. If we're going down, each one of these points going down is also 1. Think of them as intersections at a city street. There's only one way to get there. Now, let's say that I want to get to this specific red spot right here in the center. In order to get there, I have to go one way and then down, and then one way and then across. So there's only really 2 ways to get there. And you'll notice that we literally can add this point and this point to get that point. Let's go and test that thought again. In order to get to this green dot right here, right? In order to get to this green dot, let's see what would happen. In order to get there, there's one path to get there. Now we have to go right and then down and then across. That's another path to get there. And then down and then all the way across. And that works. Oh my goodness. So there's only 3 possibilities to get to that spot. And you'll notice that 1 plus 2 gives us 3, doesn't it? I'll give you a hint. This is actually another application of Pascal's triangle. So we just add up all of the interior numbers to get the diagonal. So 2 and 1 gives us 3 here. 2 and 1 gives us 3 in this spot here. And this spot, these two, this and this will give us this. So we add up all the 2 points, so here and here, to get 4 and 6 and let's see, 4 here. And just take your time and fill out the rest. Pause the video and fill out the rest. So taking these things and always adding the 2 previous corners to get to the bottom right corner will always give you the final total. And by doing so, this will allow us to say that there are 462 ways or paths to get from A to B. So there is a shortcut to find this. I'm going to show you real quick. The key idea here is to count. In order to find this, you're going to find C of the number of rows plus columns and then comma the number of rows. So in this case, I want to count the number of rows and columns. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my answer is C of 11, comma, and the number of rows. Count the number of rows. 1, 2, 3, 4, 5. And there's your answer, 462, when you punch that in your calculator. So that is the shortcut to find the answer. But when I'm asking you to do a problem like this on the test, I want you to fill out the grid and show me that that is the answer. And then to quickly check would be C of 11 and 5. So now let's try another problem where we don't have a symmetrical pattern to get to our spots. Okay. The previous one had symmetrical patterns, and so it was easy to go and find out how many rows and columns to get to our spots. But if we don't, We literally have to start from one corner and go to the other corner. So imagine this is corner A, and this is corner B that we want to get to. Here is our start, and here is our objective. So for this type of problem, we literally have to just say, okay, to get to this point, there's 1. To get to this point, there's 1. There is no other way to do it. We just go to each individual point and figure out what each point is worth. 3. 1 and 1, 2 and 1 is 3. And then for this one here, there's only one path to get here. And then 2 plus 1 gives us 3 in this spot. And then we'll pause. And then to get to this intersection here, there is only one way to get there, because if we went this way and then this way and back up, it would be going backwards. So we can't use that. So there's only 3 ways to get to this spot. To this spot here, it's only one way. For this spot, it's also only one way. Okay, so now to get to this spot in the corner, we have to add 1 and 3 to get 4. To get from here to here, there's only one way, because we cannot go from here to here and add our path. Okay, so now this is also 3. And now to go from here to here to this specific point, 4 and 3 will give us our 7. And then from here to here, going to that point, is also adding those 2. So we end up with 6. 6 plus 7 into this corner gives us 13. And then 1 and 7 to this point gives us 8. 13 and 8 is 21 into this basic corner here. And so now going along this path here, there's 21 ways to get to that specific spot, and another 21 ways to get to this specific spot. And the same for these outer spots here, 21 and then 21. So now, once we've done that, we're going to go and calculate the rest of these corners. So this part here in the center is 42, and 42 and 21 is 63. And to get to this spot from here, there's no other way to get to it. So you're literally going to have 42 again. And then 42 plus 21 is 63. And 63 in this corner again. And then to get to this specific spot, we add the 2 and we get 126. Therefore, there are 126 different paths to get from point A to point to B. All right, so basically that's what happens when you don't have a symmetrical grid to work with. You have to sit down and figure out whether you're doing any backtracking or not. If there is a backtrack, you do not add it to the next corner. So your homework for this lesson is page 256, number 1 to 10. You can find that as lesson 4 in your day package. Okay, good luck, guys.